All right, so once we've gone through all of the GCF stuff, primes and composites and things, knowing how to sort of break down these numbers, it's going to allow us to take a given fraction and reduce it to lowest terms. And so this is sort of built on a couple different properties, right? So recall that one of our sort of main fraction properties is the idea that like a fraction, sort of a over a, is equivalent to 1, right? 1 whole, 5 over 5, 6 over 6, 7 over 7, 20 over 20, 19 over 19, right? All of these things reduce down to 1. It's equivalent to 1 whole. So what that means is, so if I have a fraction like 10 over 15, for example, right? What this allows me to do, I mean, certainly just conceptually this means, right, every whole value is broken up into 15 parts, and then this sort of fraction represents 10 of those 15 parts. So what's the size of it? So in theory, right, what we can do is we can sort of break these numbers down, 10 and 15. You can sort of do this with a factor tree. These each just sort of break down into 2 pieces, right? 10 is going to be 2 times 5, and 15 would be 3 times 5. And so when we do this, what happens is we have essentially sort of a matching pair, 5 over 5. Technically, right, when we're sort of like running through things, what we could do here is sort of write this as 2 over 3 times 5 over 5. We can kind of break this up into 2 different chunks, and then the idea here is that 5 over 5, right, becomes just 1 whole. So this sort of becomes 2/3 times 1, which is going to be 2/3, and that would be our reduced version. That's conceptually what's happening, right? So we sort of have this idea where we have sort of a matching factor on the top and the bottom essentially becomes 1 whole. And so 2/3 times 1 is just going to then be 2/3. And so what we've done is we've taken sort of our sort of essentially, this kind of ratio in some sense. We'll be talking about those officially later, right? But this sort of like 10 out of 15, right? 10 to 15 kind of comparison. And it sort of reduces down to the equivalent of 2 out of 3. Visually, in some sense, if you broke something up into 15 pieces and you have 10 of them, you could sort of have instead broken it into 3 pieces and taken 2 of the 3 pieces, and you'd sort of have the same amount of the whole, right? You'd sort of be representing the same sized thing. So there's lots and lots and lots of different ways to do this. Once we kind of see the strategy here, the way I usually sort of go about it, right? So let's say we have something like 18 over 24, right? What I'll do is the same kind of thing that we did up here. So I'll break each of these numbers down into their prime factors. Or you can be a little strategic about it and you can kind of look for just common factors, any kind of common factor that they share on the top and the bottom. And the idea, again, right, is if you have matching terms on the top and the bottom, they kind of, come out to the side, 5 over 5, which really just becomes 1. You can also think of this as a sort of division property where if you have 5 divide by 5, you're going to just end up at 1, right? And so then you sort of end up with 2/3. Let's break these 2 down. We'll kind of do this a couple different ways as we go. There's not really any sort of better or worse way to do it. So maybe we'll just sort of do these a few different ways, and when you're doing them on your own, you can kind of pick and choose a little bit how you want to do it. Let's break these all the way down. So like, for example, 18 would be 3 times 6. 24 you could do, right, like 2 times 12. These numbers will break down a little bit more, right? So 6 would be 2 times 3. 3 times 2 times 3. Right, 12 would be kind of 4 times 3, and then that would be sort of 2 times 2. So what we can do to say this 2, and then the 12 would be 2 times 2 times 3. And so what I'm going to do here is I'll sort of write this a different way. So in theory, right, we can kind of pull any of the common terms out. So you could see sort of, right, 3 and 3 and then 2 and 2. I think the way I sort of tend to do it, I mean, conceptually this is what's happening, but just sort of notationally, I kind of tend to do more of just like a cancel thing, right? Every kind of one individual number on the top is going to sort of cancel out the same number on the bottom. It's a 1-to-1 rate, right? So sort of this 3 will cancel this 3. Same kind of thing, right? I can do the 2 on top cancels one of the 2's on the bottom. And then at that point, I'm pretty much out of common terms, right? So what's left over here is 3 and then 2 times 2. So this is 3 over 2 times 2. And so this becomes 3/4, 3/4. And then that's going to be my final. So reducing is about, right, sort of breaking our numbers down in this way. So trying to sort of break them down to lowest terms, break them down into their individual factors, and cancel and sort of divide away any of the common factors. What we're going to end up dividing away in the end is the greatest common factor. So if we think of 18 and 24, their GCF would be 6. So in theory, this is 3 times 6. This would have been, right, 4 times 6. So you could have sort of jumped right to 6 and 6 and divided them away, and you'd be left with then 3/4, which would be our sort of final answer. If you can jump right to the GCF and divide it away, all the better. I mean, that would be sort of even a little bit faster than what we just did. But it depends on the numbers, and it sort of depends how you see it just, on that given day and sort of at that moment. Sometimes, different factors stand out more than the other. And it just kind of really depends, honestly. Let's do a few more. Let's do maybe an improper, right? So how about, right, 56 over something like 42, maybe. So 56 over 42. And what we'll do is, let's just sort of break this down. So 56 would be maybe 7 times 8, something like 42. Be 6 times 7. These numbers will break down a little bit more. So I suppose just for sort of the sake of thoroughness, right? So 8 would be 2 times 2 times 2. 6 is going to be 2 times 3, and then times 7. So what we're going to do is just the same thing we've been doing, right? So if I have any sort of overlapping factors, right? So 7 and 7, sort of one from the top, one from the bottom. Those will cancel. And then similarly, right, sort of 2 and 2. So what's left over for me here, I have 2 times 2 on top, which is 4. And then I have this sort of 3 left over on the bottom. So now I'm going to get a 4/3. So this kind of a reduction, you could sort of make the numbers sort of as big or as small as you want. It doesn't particularly matter. The idea here and the advantage is you're trying to sort of reduce them down to lowest terms. So you're trying to kind of cut them down to the smallest possible version of this fraction, if only because it's easier to sort of conceptualize and kind of visualize a smaller number than a bigger number. So if we can do that, it just will sort of help us, do anything else with these numbers, even just, right, sort of think about how big they are. We haven't sort of seen any fractions that look like this, but in theory, this same kind of principle, this reducing principle, is possible to do if you throw variables into your fractions also. Make them sort of expand them not just from fractions, but expand them into what we would call a rational expression, which is a fraction value that has some variables in it. So if I do something like 20a squared b over, right, 35ab cubed or something. What you're going to do here is take the variables and break them down and sort of expand them in the exact same way that you're doing with the numbers. So in the same way that we're sort of breaking the numbers down into their individual factors, we'll sort of treat the variables exactly the same. So for us, we'll just kind of do all these things at once, right? So 20 would be something like 4 times 5. A squared, right, would be sort of a times a, and then b obviously is b. 35 would be 5 times 7, and then, right, individual a, and then b cubed would be 3 b's all in a row. Notice, of course, right, so 4 we could sort of break down a little further, and maybe I'll just sort of do that right where we are, right? So 4 would be sort of 2 times 2. watch your notation a little bit here. If for example, you don't necessarily want to sort of write that whole expression over again, which you can sort of tell. Obviously, I didn't really feel like doing that. Just to sort of change this one thing. Cross out the old term and sort of write in the two new terms, right? Never sort of leave the 4 there, because if you're going to cancel and work with these numbers, you need to make sure that you're sort of excluding stuff that you've rewritten. Once we have it here, we'll just do sort of the obvious thing, right? So the number cancels the number, so 5 cancels 5. I guess I didn't even really need to break the 4 down into 2 times 2, because it wasn't going to cancel away anyway. But, just to be consistent with what we were doing before, why not? As far as our variables go, excuse me, same kind of idea, right? So any sort of single variable on the top will sort of match and cancel with the same variable on the bottom. So for us, that's going to be A cancels A. I have sort of then one A left over in my numerator, and then sort of B cancels B, and that leaves me with 2 of these B's left over in the denominator. If I kind of maybe rewrite just sort of the leftovers, so this is 2 times 2 times A in my numerator, and then this is 7 times B in the denominator. Sort of remultiplying the leftovers here, this is going to be sort of 4A over 7B squared. Right? So we can sort of rewrite any of our variables that sort of double up, right, show up more than once. We can sort of rewrite them with exponents. Obviously, we're sort of canceling and reducing first, right? So any kind of common terms we're sort of reducing out, including common variables. Let's maybe do sort of one more with some variables. We'll maybe do some x's and y's and z's. We'll go from here. How about maybe something like, I don't know, 60 x squared y over 15 xy. Let's do something like this. If I start to pull these apart, 60 would be what? 6 times 10, right? X squared would be x times y. 15 is going to be 3 times 5 times x times y. I have a couple variables here that I can sort of see right away. We'll cancel out. X cancels x, y cancels y. This x is going to be left over. Initially, I don't see any overlap with these numbers, but if we think of the numbers up top, 6 and 10, both of those are going to break down a little further, right? So maybe we can sort of just do that while we're here. So 6 would be 2 times 3. 10 would be 2 times 5. So then that allows me to sort of say, okay, so 3 cancels 3, 5 cancels 5, and so I'm left with, hopefully this isn't getting, it's a little bit cluttered. Let's sort of rewrite what all we have left over. 2 times x. The bottom, literally everything is canceled away, right? 3 has canceled, 5 has canceled, x has canceled, y has canceled. What's left over, right? So this is essentially division, right, and sort of multiplication. So when I divide things away, if I divide everything away, what I'm left with is 1. I'm not left with 0. I'm not subtracting. I'm left with a 1 on the bottom. If I divide it away and ended up with 0 on the bottom, that's going to be undefined, right? Sort of catastrophically bad. So that's not what we're dealing with, thankfully. In this case, I have 2 times x. So that's going to be 4x over 1. Well, that would really just be 4 times x, essentially sort of unfractionized, right? So it sort of was a fraction, but now if my denominator is just 1, I can write my final answer without a fraction bar at all. I just get a 4x, and then that's the final. So we can cancel variables just in the same way that we're canceling our numbers. It's just a matter of sort of expanding out and then sort of just canceling one to one from the top and the bottom. And that's the idea. Lowest terms.